Hey and welcome. Today we are going to solve design HashSet interview question. We will implement a really handy data structure, so consider this as a gem. Let's get into it. Here we have the sequence of operations that is going to be thrown to us to handle. From first look to this, we will have three operations. So at the first step, it will initiate my HashSet instance. Then it will call add method with 1, output should be null. Then another add with number 2. Next is a contain check for number 1. Then another contain check for number 3. We don't have it. Now here starts two important flows to challenge our HashSet. First one is it adds another number 2 again, but we should do nothing about it. This is the biggest feature of HashSet, ignoring the repeated values. Again, another contain check for same number 2. Here comes the second important flow. It will invoke the remove method for number 2 in the next step, and it just wants to make sure that we are remove number 2 properly, and we are not holding two instances of number 2. Okay, let's see how we are going to implement this. Let's break some ideas about HashSet and move forward step by step. We need to implement an array-like data structure that its main focus is about one important thing. All values are unique, no duplicates are allowed. Basically, to keep a rigid state of only unique values, the simple solution is that for each value that is going to be thrown at us, we need to have a mechanism to check if we already stored that value or not. And only if not, we will take care of it. That's our first observation. However, there are some other logics to handle this uniqueness. One boundary we have is the length of this hash set. Obviously, we cannot have an infinite length hash set. There has to be a max boundary for it. In case of this implementation, we will choose a small value, mainly to be in the safe side with space complexity, but that small value has some fundamental thought behind it. We will get back to this later. But how we are going to store items into this hash set? From question's description, we should have three methods for our hash set implementation. So calling my hashset.add some value should store it somewhere. And this somewhere will be anywhere within that array-like data structure that we discussed. Let's take that somewhere as a simple array with lengths of the same n for now. So that is the first principle of our hash set. Initially, it's just an array, but we are not just simply adding values directly into this array. This array right here will hold a bucket for each of its indices. These buckets, plus the way we access them in every index, are the magic parts of the hash set. But there are two ways to instantiate these buckets. First, each bucket could be the head node for a linked list. Second way is they could be the root node of a binary search tree, which could be a whole different video on its own. But as a quick note, binary search tree in this case brings us more optimized logarithmic time complexity for operations compared to linked list. In our case, we will stick to the linked list for now, but how we are going to access these buckets' values? Okay, this brings us into two main concepts about hash sets. First is something called hash function. Remember this array? Let's say we have 5 buckets in it. Now think of hash function as a thing that, based on the given value to it, it will simply going to give us an address within that array based on some logic. And this logic could be just as simple as a modulo operator in between of the given value and the length of the array, which will be fine for the scope of this problem, or it could be complex as these ways. I'll put the link in the description for this article for you to read it out. Second is, the main purpose of this function is to resolve something called a hash collision. So new term here, what is it? A hash collision means for the given value, the hash function will return a bucket address that already has been used once or twice or however many times before. Let's take the same example. The n is 5 and we have already placed number 6 in this bucket, but the modular result of numbers like 11, 16, 21 and so many other numbers are also 1. That is a hash collision. The hash function returns the same bucket index for multiple values. What will happen in that case? Well, for that, we will leverage the linked list aspect of our buckets that we are going to implement. That is how we are going to escape the hash collision. And guess what? Remember that I said we will come back to how we are deciding about the length of the underlying array for hash sets? Well, in case of number 5 here, of course we will have collisions so often. But the point here is how we can reduce this collision from happening as much as possible. Here's the part that prime numbers comes to survive us. Because basic math, they are only divisible by 1 and themselves. In order to have a reasonable, or better to say scale for our hash set, we will choose a prime number. Now it's up to you. As much as bigger prime number you will choose, the less and less collision you will encounter. So that is why you cannot just choose even or odd number, or better to say any number. It has to be a prime number. But what about the implementation itself? Well, we need three things here. First is a simple array that holds the buckets for us. Second, we need a bucket structure which will hold a dummy linked list head node to help us in iterating over that linked list. More on that in the code. And lastly, we will need a simple node data structure for linked list nodes. And we will build our HashSet class based on these three things. Now let's implement it. For implementing our hash set, we will start from writing the code for bucket structure first. But since it will be implemented based on a linked list, we need to code up a single node for linked list. And for that, we will use a constructor function in JavaScript. This node function will receive and hold only two things: the value for the node and a reference to the next node that it points to. The next value will be null by default. So that was it for node. Now let's move to the bucket. This bucket will initially hold the dummy node node as its head, and it will help us in iterations through the linked list that it represents. Okay, now this bucket constructor function will have three methods on its prototype: exist, insert, and deleting respectively. We will start from exist because we are going to need it in insert. We need to check for a value's existence before we insert it. To implement exist method, it's just a simple linked list iteration to check every node value. I have a bunch of linked list videos if you want to learn more about, but the idea is that we hold a reference to a current node, and as long as that current node has the next value attached to it, we will keep asking its next value. And meanwhile, we will check the value of that node, and of course, if the given key is the same as node's value, we will return true because it exists. Otherwise, we will move to the next node. And finally, we will return false in case of if we didn't find anything. Okay, next up is insert method. Now the exist method on the bucket comes to help us here. So if the value not exist in that bucket, then and only then we might create a node, then add it to the bucket. Just note that for the created node, the next value will be the next node that current head refers to, and the current head will point to this newly created node. And literally by doing that, we just squeeze the new node in between the dummy node and the null node that it was pointing to. Now the last one, the delete method. And for this, we will use a dummy head node to serve as a prep variable initially, and one current variable pointing to the next value of that dummy node, which in fact is the first real value in the bucket. Then, as long as current variable holds a node, we will do our search work to find the target value. And if we find a match, we will attach the pref nodes next to the current node next, literally skipping the matched node and connecting its left and right neighbors together, and then return immediately because we are done here. Otherwise, we will move through the iteration and finally return null. Now we are done with both bucket and node. Let's use them to implement the hash set. Initially, we need to define our limitation, or better say the size of our hash set array. We will call it the key range and assign it a prime number that is big enough to satisfy the limitation of this problem. We will choose the first prime number that is less than 1000. Then we will create our buckets array, and this array will be the same size as of our key range variable. We will do a loop as big as our key range to instantiate one bucket object in each index of that bucket's array. Great. Now we need to create our hash function. We will assign it to the prototype of my HashSet class to access it through this keyword within our other methods. And it will be the modulo of given key on the key range scale we defined earlier to map the key to an index within that bucket's array. So now we are so ready to create the real methods that is going to be tested. For add method, first we will try to find the index we want to add the given key using hash function. And based on that index, we know that every element in buckets array is a bucket object, which has the exist, insert, and delete method available to us. So we will use the insert method of it. And it's the same for remove. First map the given key to some index in buckets array with help of a hash function. Then use the delete method on the founded bucket for that index. And finally, contains method is the same again. Map the given key to an index, then use that index to check existence of the given key. But this time, we might return the Boolean result since we expected to do so with contains method. Well, that was it. Now, if I run this, test cases are passing, and if I submit, seems like we are in a good shape here. Let's go back to slides for time and space complexity analysis. So the time complexity will be O of n divided by k. N will represent the number of values and k will represent the number of buckets, the same prime number we choose. If we assume that all given values are distributed over buckets evenly, then we might expect that time complexity, because then in the worst case, we need to scan the entire nodes in one bucket to find the target value. And the space complexity will be O of k plus m, which k will be the number of buckets and m will be the number of nodes we added to those buckets. So that was it for this video. Thanks for watching, and please leave a like, comment, and subscribe to the channel. I will put a few more links about different playlists in the description for you to check it out. And finally, hope you enjoyed this video and stay tuned for the next one.